Hello everyone, in this lecture I am going to explain evaluation of triple integral using given region. In that we have already seen type 1 region, that is if a region is bounded by sphere. Now in this lecture we are discussing type 2 region, that is if region is bounded by cylinder or cone or paraboloid. And we know that sometimes it is not easy to find the value of triple integral using Cartesian coordinates only. So that time generally we are using conversion, that is we have to convert our Cartesian coordinate system into the polar coordinate system, and after that generally we are evaluating this. So here also, if a region is bounded by cylinder or cone or paraboloid, then we are converting our Cartesian coordinate system to the polar coordinate system by using this substitution, and the substitution is we have to replace x by r cos theta, y by r sin theta, z equals to z, that is z by itself, and dx dy dz equals to r dr d theta dz. And we are using this substitution if region is bounded by cylinder, so that we are calling these coordinates as cylindrical coordinate system. Now depending on that, we are solving an example, and the example is evaluate triple integral of z square dx into dy into dz over the volume bounded by the cylinder x square plus y square equals to a square, and the paraboloid x square plus y square equals to z, and the plane z equals to 0. Now here we have to find the value of this triple integral, and we have provided the region of integration is the cylinder, paraboloid and plane. So first of all we are writing this region of integration, that is given region of integration is bounded by the cylinder x square plus y square equals to a square, the paraboloid x square plus y square equals to z, and the plane z equals to 0. Now we have to find the value of this triple integral. For this it is not easy to find using Cartesian coordinates only. So that first of all we are converting this Cartesian coordinate system into the polar coordinate system, that is cylindrical coordinate system. So for this, first of all we transform the given integral to cylindrical coordinate system by putting x equals to r cos theta, y equals to r sin theta, z equals to z, and dx dy dz equals to r dr d theta dz. So first of all, we are converting our given region of integration into the polar system. That means our first equation of cylinder is nothing but x square plus y square equals to a square. So after doing that substitution, we will get r cos theta square plus r sin theta square equals to a square, and which implies that r square equals to a square, because here we can take r square common. So in bracket only cos square theta plus sin square theta is remain, and the value of this is 1 only. So at RHS side only r square theta is remain. So this equation becomes a r square equals to a square. Similarly, if you take second equation, that is equation of paraboloid, that is x square plus y square equals to z, then this will implies that r cos theta bracket square plus r sin theta bracket square equals to z, and it also implies that r square equals to z. That means LHS is same for both the equation, so that this r square will be common. So this equation becomes a r square equals to z. Similarly, if you take this third equation, that is equation of plane z equals to 0, then it will becomes as it is, because we are replacing generally z equals to z only, so that here this equation will as it is. Now this is the conversion of region of integration into the polar coordinate system. Now we are finding limits firstly. So for this we have drawn this figure using that given region of integration. So in this figure we can observe this is our cylinder, that is nothing but x square plus y square equals to a square, and this curve is nothing but equation of paraboloid, and this is nothing but z equals to r square is in the polar form, and z equals to 0, that is our xy plane, that is this. So now we have to find the limits of r theta and z using that figure. Now first of all we are finding the limits for z, and for this we can observe these two equations, that is r square equals to z and z equals to 0. So in both the equation our z is present. So the lower boundary for z is z equals to 0, and the upper boundary for z is z equals to r square. So that will be the limits for z, so that we can vary our z as z varies from z equals to 0 to z equals to r square. That we can observe in this figure also. Now we are finding the limits for r, and we can observe our radius is starting from this origin and ending at this circular part, and the radius of this circular part is r equals to a. So our r varies from r equals to 0 to r equals to a. Similarly, your theta is moving in whole the plane, so that theta varies from theta equals to 0 to theta equals to 2 pi. Therefore these are the limits of z, r and theta. So that using that limit we are solving now triple integral, and therefore the triple integral can be written as I equals to triple integral of z square dx dy dz that we have given. Now we are converting this into the polar coordinate system using that limits. So the limits was theta is from 0 to 2 pi, r is from 0 to a, z is from 0 to r square. And after converting this system into the polar system, it will get z square as it is into dx dy dz is nothing but r dr d theta into dz. Now according to the integration, we are arranging this z square into r dz firstly, after that dr, and after that dz, d theta. Now we are finding one by one integration. So here first of all we are taking integration with respect to z. So here that time r will be constant, so I am taking it outside, and integration of z square is z cube upon 3, and for this your lower upper limit is z equals to r square and lower limit is z equals to 0. So after putting upper limit and lower limit, we will get r cube raised to its square, that is r raised to 6, and this 1r, that is r raised to 7. So r raised to 7 I am writing here, and this 1 upon 3 I have taken common to all the integration, so it will be outside. Now we are taking integration with respect to r, and here integration of r raised to 7 is nothing but r raised to 8 upon 8, and upper limit is r equals to a and r equals to 0 is the lower limit. So after putting this upper limit and lower limit, we'll get a raised to 8 upon 8 minus 0, and in the next step I'm taking this 8 to the 8 to the power 8 upon 8. Whole is the constant for this theta, so that I'm taking this to the outside the integration. So only 1 is remaining in that integration. Now integration of 1 with respect to theta is theta only, and upper limit for this is theta equals to 2 pi and lower limit is theta equals to 0. So after putting this upper limit and lower limit, we'll get only 2 pi, and this calculation becomes a raised to 8 upon 24. So a raised to 8 upon 24 into 2 pi is nothing but pi a raised to 8 upon 12, and that is our final answer.